Welcome everyone to today's webinar on gas detection, bridging the gap with critical thinking. Now, before handing things over to our presenters, I'd like to point out that while everyone is currently muted now, you can still type questions into the chat in the upper right-hand side, and we'll answer them all at the end. Our presenters today are Rebecca Bedell with Draeger Inc. and Drew Hinton with Aero Safety. Rebecca is the Business Development Director of Safety Consultant for Draeger Inc. in the United States. She's worked in the refining industry for Marathon Petroleum and consulted for various chemical and manufacturing facilities. Her most recent focus has been on safety optimization and sustainability solutions. Rebecca holds a BS in kinesiology and MS in occupational health and safety and environmental management, and she is currently pursuing a master's of jurisprudence in energy and environmental law. Mr. Hinton is a seasoned EHS and medical professional with over 15 years of progressive experience in occupational health and safety. Drew's the current president and CEO of Aero Safety, LLC, safety consulting and training firm based out of Glasgow, Kentucky. Now, his previous experience includes over 10 years as a career firefighter, EMT hazmat officer in Louisville, Kentucky, construction safety and health contractor for NIOSH, and various senior level positions for companies across the U.S. Drew currently serves on the Hazmat Society's Training and Education Committee, Institute of Hazardous Materials Management's Nomination Committee, and various NIOSH safety councils. So, without further ado, let me now hand it over to Rebecca and Drew.
Thank you, Ryan. And good morning and afternoon to everyone who is joining us today. We like to thank you for joining us. And, last time when we started this webinar series, we introduced more of a critical thinking concept to safety. And so today we're going to take that approach, but we're going to take it into gas detection by discussing some gas detection competency. Gas detection competency is vital not only to your confined space entry, but to your entire safety process and management plan. There's actually quite a lot we have to discuss when it comes to gas detection competency. So today we will be focusing on the types of monitors and their functionality. Now on our next webinar, we're going to dive deeper into which monitors to use and when, and the limitations of gas detection as well. So stay tuned for that next webinar. But today we'll focus mostly on types of monitors and functionality. To get us kicked off, we're going to do another exercise similar to last time. If you can get out your phone and go to www.menti.com, and you will type in this code here at the top of your screen, this 96812758. And we're going to engage in a couple of questions here and answer the question that you see on your screen. So Lindsay always performs a gas test before issuing a hot work permit. Today, she did not. What are some reasons why? Oh, we're going to see some good things come up on the screen.
It's good.
Oh, a lot of similarities here.
Mm-hmm. It's like forgotten in a hurry is in some of the top ones here.
Unit out of battery. All right. Complacency, a lot of in a hurry. Give about 30 more seconds and see what else comes in. There we go. Starting to get a well-rounded potential root of a problem type answers.
Out of cow gas is a good one.
Mm-hmm. So I like everyone to kind of take notice of not only the differences in the answers that we're seeing, but we're seeing everything from personal behavioral choices to upper management leadership answers to equipment issues, technology issues. And that's something that we want to be keeping in mind with critical thinking, is sometimes it's not just a straightforward one single answer. Sometimes it can be a combination thereof. But there are a lot of different reasons for issues to arise. And it's important, especially as us in the safety profession, take the time to think through what might be contributing to a potential issue. All right, so we're gonna get started back into the PowerPoint here. So these are some of the considerations that we're going to highlight about the different types of monitors and their functionality. Do we understand how their functionalities apply not only to exposure sampling, but how do they apply to the day-to-day operations? So Drew is actually going to get us going with gas detection responsibilities.
Sure. So as Rebecca had mentioned, there's a lot more than just simply grabbing a meter. There's a lot more than just turning it on and seeing if it says anything. So we're trying to get into, as it says, the critical thinking, the critical aspect of the gas methodologies, gas detection methodologies. And so before we jump into the responsibilities, I mean, it's important for me, as a person that's working in the hazmat field and the first responders, and also now I'm in the private industry, it's when I'm going into confined spaces and working with people going into confined spaces, that we understand where we've came from, right? And so if you're not familiar with, the days of the Davy lamp, to where they use that in the mines, they would use a flame to detect, flammable atmospheres in the mines. And you would hold the lamp and air would pass through it. It burned off, typically vegetable oil. If that flammable gas mixture was present, the flame would burn higher with, some kind of blue tinge usually. But if the atmosphere was oxygen deficient, the flame would go out. And so that methane air flame mixture was typically around 17% oxygen at a minimum. And so if that flame went out, that was their ideal signal to evacuate, and while they had enough time to do so. And so going now forward to where we're in present day, these meters take a lot of things out of it, but there's also a lot of things that we as the user, we as the meters user, have to understand what it's actually telling us. So it may tell us, like on this meter that we're seeing on the picture here, 5 different gases, but it's telling us a whole lot more than just those 5 gases. And so gas detection responsibilities, in a nutshell, personnel that's involved in this should be able to perform the following, which is bump test and calibration, and we'll talk about the difference between those two here in a second. Battery replacement, if it has rechargeable batteries, or if it's a taking out AA batteries, putting those in, however that's set up, and then some basic sensor replacement. Some things you may be comfortable doing, some things you may not be comfortable doing, or you just don't want to mess with it, and you send it off to an authorized repair center that whatever you're comfortable with, and get those replaced, but at least knowing when that sensor needs to be replaced. And then also you have to be comfortable with the tubing and attachments. And so every meter has got some kind of limitation. And what we're getting ready to talk about, active versus passive meters. And so the ones that have the internal pumps that are typically used and more so used and recommended for confined spaces, so I can attach tubing to it, there's only so much tubing that I can attach to that. It's not that meter, or that pump inside of that meter is not an indefinite amount of supply. It can only pull so much in there. So understanding those, understanding your attachments, how much time to add to my response time. So that our meters response time we're talking about now. We'll talk about that more in depth a little bit later, but we're talking about our T50 or our T90 response times on our meters. So some people I talk to, they're like, I mentioned T90 and they're completely clueless. And some people say, oh yes, we make sure that this is covered during our training. And this is something we need to understand so that we know how long it takes for that meter to get an approximately accurate reading. And then applicable OEL, so occupational exposure limits. Do I know what that PEO, that permissible exposure limit set by OSHA is? Do I know what NIOSH's recommended exposure limit, or do I know what the TOVs are, the STLs? So we can go on and on about alphabet soup, but do I know what I'm working with and what those specific limits are? And then understanding your sensors in your meter, right? So if I have, this particular meter we see here, it's got a carbon dioxide, CO2 sensor, it's got a methane for measuring LEL, oxygen, sulfur dioxide, hydrogen sulfide, and CO. And so we've got several different sensors on there, understanding what those sensors are, how they operate, and we'll get into the next webinars. We'll go really in depth with how they actually operate, but understanding that one meter that has a methane sensor measuring LEL may work completely different from somebody else's meter that has the same that measures the same thing, but it's got a different sensor in there that has different technology. And so understanding those things is going to be crucial for our gas detection personnel.
Absolutely, Drew. And for anyone who was on the previous webinar on the confined space critical thinking, you might remember how we touched on the importance of understanding and thinking through, your atmospheric testing points of getting a full representative sample in the high, mid, low type space. And we will go into that a bit more, but you can see how these responsibilities are strongly correlated in understanding your gas detection technology that you're utilizing so that you can accomplish that thorough safety assessment and get a true representative sample to determine whether an atmosphere is safe for entry or for hot work or there forward.
Absolutely, absolutely. So we kind of touched on the difference between, or the technology and terminology between active versus passive technology within your gas meter. So they all have a little bit different technology, and they all have their time and place and the way they work best. And so if we're looking at an active gas detection technology, it does have an internal pump on there. So you can see in the top picture where they have tubing attached to it, that's typically where you're going to use that. So if we're talking about confined spaces where we're making a vertical entry to where we're going to have to drop that tubing down inside the space, this is what we're going to want. We've probably all heard stories, and maybe you've even seen somebody that's taken a meter, tied it to a rope, and put it in there and dropped it down real quick, pulled it back out. That's not how things work. That's not how we should be doing things. So this active pump or active meter has an internal pump on there. It's, like you said, best for monitoring outside the space by the attendant as well, because I can just drop that tube down inside that space and I'm getting readings continuously. And so I can get my pre-entry readings. I can have my continuous monitoring by that attendant or hole watch, whatever you want to call that person. And then understanding the next bullet point is your response times. Again, it's not as simple as just taking that meter out, firing it up, and seeing what it says. You have to understand what that response time is. And so we're going to talk about a couple slides later. We'll talk more about those T50 and T90 response times. And those are all specific to your meter. They're specific to your sensor of your meter. So you may have a meter that shows a T90 response time of 10 seconds for your, let's just say, oxygen sensor, and it may have one that shows 20 seconds for your LEL sensor. And so they're all different based on what you're actually measuring and the type of meter equipment that you have. And so on the opposite side of the spectrum is your passive meter. So this is ones that typically people use for their personal meters, like you see on the bottom picture. The person has the meter attached to their pocket on their coveralls. And so typically they'll take them, if they're going into a confined space, the entrance will take this with them, attach it to their coveralls, attach it to the harness, whatever it is, so they can measure real time where they're at within that space. And so this can be taken with them. It helps them understand versus, rather than just the tube dropping down into the space, they can understand where that's actually at. But what's critical for this is placement. I've personally watched people go into a confined space and have to stop them and say, hey, your meter's turned around backwards. You've got it to where the sensor area where it's actually drawing in the air is facing to your chest. So it's blocking off the inlet. So making sure we're placing in the proper area. And again, it's best for, as you can see here, personal, and you can also set those up for area air monitoring. So if we've got an open confined space, let's say we're getting the construction side where we have an excavation or trench that would be, depending on the depth of it, be considered confined space. I may be setting these up, or if I'm setting these up outside of a confined space, let's say it's some kind of a hazmat situation and there's a leak, and I'm wanting to see how far that leak has progressed or how long that leak has delineated away from that tank. I can set up this area air monitoring to where it's going to monitor in those specific areas wherever I set that up at.
Absolutely. And on the placement, a question I get often is what constitutes your breathing zone? And I've heard a couple different explanations, but back to that, placement is crucial. One of the things we can say for certain is if your goal is to protect and have a personal monitor placed within an employee's breathing zone, One place that it should not be is on the back of the hard hat behind their head. But as Drew mentioned, it's even more important to make sure that the sensor is not covered up. So it's not inside the pocket where it couldn't be receiving or detecting that gas. So those are things to keep in mind as you make those decisions for your workforce, and especially those who are going into potentially hazardous atmospheres.
And so jumping into, we talked about earlier, the calibration versus bump test. This is something that anybody using any kind of gas detection equipment, whether it's an area meter, whether it's a personal meter, whatever kind it is, you should be familiar with how to do some basic maintenance on your metering equipment. And so your bump test is something you should be doing prior to every single time you use it. Now, of course, if you're not using it that day, it's just sitting on the shelf. No, you don't have to go grab it and do it. That's just extra work that you're having to do. But every time you go to grab that, whether it's a confined space, a hazmat, whatever situation it is, you need to be doing a bump test. So this is testing strictly for your alarm triggering. That's making sure that, okay, you're going to expose it to a certain gas with certain concentrations. You're just exposing it to that gas, a known concentration of that, and it's going to say, okay, I've got CO, my alarm's going to go off for carbon monoxide. I got H2S, my alarm's going to go off. It does not check accuracy. It simply checks to make sure that it is able to detect that particular gas. So typically takes 15, 20 seconds. And then your next step, if your bump test fails, or depending on your meter, whatever meter you have, depending on that model, it'll tell you the minimum amount of calibrations you should do. And so this full calibration is that's where you're actually going to check for not only your triggering, but also you're checking for your accuracy, and it's going to help you correct that. And so if I have a cylinder of calibration gas that's got 25 parts per million of CO, 100% of the LEO, whatever it is on the label of my cylinder, it should be matching it up when I expose that to my meter. And so if the calibration gas cylinder is supposed to be showing 25 parts per million of CO, and then when I expose it to my meter and it's reading 50, then there's an issue there. And so this calibration is going to correct that issue. Sometimes it does, most of the times it does, I should say. Sometimes it doesn't. Sometimes there's an issue with the meter itself. Maybe there's a failed sensor, there's something wrong with the internal circuitry, but maybe there's something wrong. But a lot of times this will fix that and correct that. And so again, it's checking for the triggering of the alarm itself and the accuracy. It takes usually 1 to 2 minutes. They're all a little bit different depending on what meter you have, but it'll walk you through that. It'll time you down, and you can watch the readings on the display, and it'll show you. And so if you use something similar like the docking stations you see here, it's almost fail-proof. Like you just put it on there, it'll walk you through the whole process and does all that for you. But you can also manually calibrate it yourself. If you wanted to take that cylinder off, get a different regulator, and then attach it to the meter, you can do it that way as well. But the frequency is depending on, again, not only the sensors that you're using, but also your operating conditions. And so if I'm, a lot of meters, I'm not going to say all, but a lot of meters will tell you to at least calibrate at least twice a year, maybe every 6 months. And so that's typically at a bare minimum. But if I'm using it all the time, so I've got a history in the fire department. We're going into house fires literally every shift. If we're exposing it to high concentrations of carbon monoxide or high concentrations of hydrogen cyanide, whatever it is, I'm getting known concentrations on a daily basis, several times a day, then I may have to calibrate that, weekly, monthly, whatever it is. You just don't want to over calibrate that because you can decrease the life of your sensor. So you need to base it on what your actual operating conditions are, and then reference your user manual for the particular meter that you have and base it on those sensors.
Yeah, absolutely. And I see that a lot myself, or saw that a lot myself with refining as well. We used them quite frequently. And our routine at that point was calibration weekly, obviously a bump test every shift. But it depends and it varies, but you obviously want to make sure that everything is functioning properly, because you certainly don't want to get out to a potentially hazardous area and the meter not be performing as expected.
Exactly. And so we'll get into some basic troubleshooting. We're not going to qualify and certify everybody as authorized repair technicians, but there are some things that you as a user of your meter should be able to understand, that when things go wrong, just some basic things go wrong, how to correct those issues, what may be causing that issue. And so we're looking at some, are we getting abnormal readings, right? If we're getting abnormal readings, what is that normal? How do we know it's abnormal? So we have to understand what is normal in the first place. And so we're going to understand that based on, one, our ambient air concentration. So if I'm just taking a meter out in an area area of sampling, or if I'm doing it outside the space, what should I be getting in that area at a normal concentration? I can refer to my confined space hazard assessment. We'll talk about that a little bit later on. I can refer to my hazard assessment, my safety data sheets, whatever it is. I need to know what should I be getting there. And so if I'm getting outside of that, what is causing that? And then who's right? Is it you or the meter? The philosophy, the safe way to do it is just assume the meter is always right every single time. If it's alarming, just go ahead and assume it's right. Even if it's been malfunctioning for the last 2 weeks and it's going off unexpectedly for 2 weeks straight and it's been an issue, don't care. Always assume the meter is right until you can verify otherwise. So if I need to get a second meter out there, or I need to get that meter, if it's the only meter I have, I need to get it fixed. Whatever it is, I'm assuming that meter is right, even if I suspect it's wrong. Get out, make sure you're in a safe space. Get a second meter if you have one. If you have something of some other kind of metering technology. So if I'm using a combustible gas indicator meter sensor, and then maybe I want to go out and get a Dräger tube that'll actually measure, more or less in a mechanical means rather than electronic. Get some other kind of way of verifying that until you just say, oh, it's the meter's fault, that's wrong, and I need to go back in. So always assume the meter is right. If it's showing an error message, what is it? Is it showing that there's an error message because it's simply the battery needs charging? Is there an error message when you're doing the calibration that says the oxygen sensor did not calibrate? What is actually going on? Sometimes your user manual will give you a lot of basic information on that. You can look at the troubleshooting section and it will tell you more or less what are some common causes of that. It may not pinpoint it, but it'll give you some typical suggestions you can check for. And if are there readings that are showing up where it shouldn't? Again, understanding what should I see on that meter. And we just talked about the bump test. Did I even bump test it in the first place? So if I didn't bump test and I didn't know that it was going to work properly in the first place, how can I assume it's working right now? And so one of the things that we, without getting too crazy in depth, is making sure, one, there's an adequate oxygen content in the atmosphere, right? So fire, any kind of combustion needs typically around 16% oxygen to burn. Same as in your car. Your car has to have some kind of air fuel mixture in there. And so if you're using a meter with a Wheatstone bridge sensor or catalytic bead sensor, whatever you want to call that, it's got to have an adequate amount of oxygen content in there. And so if that oxygen content is thrown off, then so will my meter readings. If I have low oxygen content, then my meter readings might be low, because the way that works is it has to pass the gas in through these plexiglass bulbs. And what it does, it draws that sample across the exposed one. The combustible atmosphere interacts with that coating on the bead, and then it causes that to heat up by oxidation, which then creates heat. Then it creates changes of resistance, and it looks at the difference in that resistance and says, there's a difference of 2, so let's put 2 up on the meter. And that's how it works. So with it knowing that it works by oxidation, if I have a different oxygen level or a low oxygen level or a high oxygen level, my readings may be off than what it normally should be. And so that's kind of where the infrared comes into play, because they don't rely on that oxygen content. And so if I'm looking at the atmosphere I'm working at, just give an example here. Let's say we're monitoring for propane. Propane is both not only flammable, but it's also an asphyxiant. And so if I'm just pulling out a meter that shows LEL, I'm just checking for flammability, and I know I have propane, it may not work if I have a catalytic bead sensor meter in there, because it has to have the oxygen. So that's where that infrared sensor will come into play. So making sure that you have that appropriate technology on there.
Absolutely. And in our next webinar, we'll definitely get deeper dive into all of those applications as well.
Yeah, absolutely. So, looking at what your application is going to help you determine the type of meter, the type of metering technology you need, and also how you're going to meter. So we're looking at a confined space entry to where we've got some time to prep. For the most part, we got time to prep. We should have a hazard assessment completed, whether it's our site or whether we're going on to a customer site. We should be at least reviewing that hazard assessment. If one's not done, making sure that's done prior to entry. Is it confined space rescue? A little bit less time to plan. We're kind of going, full speed to this, trying to figure out what's going on, whether it's fire department, whether it's a hazmat team, whether it's in-house rescue team, whatever that may be. We don't have as much time to plan. Now they're still going to do all that they need to do, but they don't have as much time to plan on the rescue side versus the entry side. Hazmat's where you're dealing with a lot of different types of chemicals. You may be dealing with, chemical A, let's say, propane, carbon dioxide leak in a restaurant one day, and then the next day you're going to a confined space to where you're dealing with sulfuric acid and methane, all these different things. So understanding the variations of what you might be dealing with. You know, we talked about with our example or our question earlier, or about the hot work example. So if she didn't do the hot work today, why did she not do that? One of the requirements of NFPA 51B, which is the standard for hot work, is that you verify there is not a flammable atmosphere. And so how can I visually verify, or anyway verify that there's not a flammable atmosphere without a meter? There's no way. Now I can remove some of the combustibles. That's one part of it, is removing some of those flammable and combustible materials. If I got a bunch of trash and rubbish and just cardboard, I can move those away from where I'm doing the hot work. But I have no way of knowing if there's a flammable gas floating through the air. Now, because two-thirds of the chemicals in the world are going to be flammable, right? And so I don't know anything is there unless I do have some kind of metering equipment. And then how many gases need to be monitored? You know, if I have a standard 4 gas, do I have a 5 gas, 6 gas, so on and so forth. And then we talked earlier about the tubing or the wand. If I have a float probe being used, what is that adding to my response time? Do I need it? You know, what is the purpose of those wands? What's the purpose of the tubing? Am I going to confined space, going into hazmat? And so there are a few, there's a few specific industries. They have what they call a thermal conductivity sensor. And it's almost, I'm not going to say exclusive, but almost exclusive to the gas companies, since they're more or less one-trick ponies, right? So they're dealing with methane or only a handful of other gases. They know what they're dealing with. And so if you're using one of those thermal conductivity sensors, and I'm using a combustible gas indicator, you tell me you've got 65. I think we're good because we're only at 65% of the LEL. However, let's say we're measuring methane. So methane being 5 to 15% flammability range. If you tell me we're at 65, I think we're good because we're at 65% of the LEL. But we're actually, based on your meter, you're actually way deep into the UEL because you're telling me it's 65% on your thermal conductivity sensor. So the way those work is they only measure thermal conductivity. They don't measure LEL. And so the thermal conductivity is more or less the ability to pull heat away from an element. And so the problem with that is it doesn't know what kind of chemical it is. More or less, it's a dumb meter. It doesn't know what it is. It could be propane. It can be carbon dioxide. It has no idea what chemical it is. And so we have to know the chemical we're dealing with, and we have to know the flammability range of every single chemical we're dealing with in that atmosphere. Otherwise, it's completely useless. Like I said, if it sees propane, carbon dioxide, exactly the same. And so if we were going into a confined space, and let's say we had a nitrogen leak that we were using for purging that system, it would, even though yes, it's an asphyxiation hazard, it would make you think you have a flammable environment in that atmosphere when you don't. So this type of detector does have a purpose in more or less gas chromatography, but that's a whole lot. It's mostly it. So again, we'll talk a lot more about that in the next webinar series. So again, making sure that you know what you're using for is crucial.
Absolutely, and thank you for bringing up on the hot work permit thing. NFPA 51B requiring to verify you do not have a flammable atmosphere, because I've unfortunately had a lot of clients mention that they do a hot work permit, but they do not gas test. And a lot of times the answer is, well, I didn't know I was supposed to. OSHA only says I have to OSHA only says I have to gas test for hot work in a confined space. So there's a lot of confusion on that based on the OSHA standard, but not to be forgotten that there are many working regulations that apply to industry, including NFPA 51B. So I think that's a very good point, and we won't go on too much about that right now, but something to keep in mind for the future.
Yep. And so here is the gas is lighter than air. There's 13 gases that are lighter than air. And the way that I was taught in the fire department, maybe a few of you have heard it before, is the 4H medic ANA. And so that kind of, if it's a little mnemonic to help you remember the 13 gases. So you can see these. The thing about the 13 gases is there's several of these that most industries will have exposure to on any given day. And so we may have exposure to carbon monoxide from just normal combustion, no matter what it is. We may have exposure to acetylene from hot work operations. I've got customers that have ammonia for their refrigeration systems. They're using nitrogen for purging. A lot of these things on here that we may be exposed to. And so that 4H medic ANA is just a way to remember those 13 gases that are lighter than air. And so again, are you getting readings where you shouldn't expect to, or OSHA recommends testing at 4-foot intervals in vertical types of confined spaces. So we drop that down and we do those, we get our measurement, wait for our appropriate response time, drop it down 4 more feet. So that's in vertical spaces. And so it's important that we understand what that T90 or T50 response time is for our particular sensors. And so we mentioned earlier about 2/3 of your chemicals are flammable. And so while they may have different flammability ranges, it's important to understand that concept so you can know what to expect and really what precautions to take. And so just looking at these here, hydrogen on this list, but also let's use methanol, for example. Those burn clean, right? So we may or may not see any kind of flame with that. You may see a methanol flame at night, but during the daytime, you're probably not going to see either one of those, methanol or hydrogen. During the day, it will be very difficult. So it may be difficult to see that unless you unless you have a thermal imaging camera or something to actually see that heat source. So you don't want to get inside of that burn atmosphere. And it's also important to understand that while we're focusing on these gases and that 2/3 of those are flammable, that those flammability ranges are most of those are based on what they call NTP, is your normal temperature and pressure. Some of those are based off STP, which is standard temperature and pressure. And the only difference between those two is 8 degrees Fahrenheit. And so NTP, normal temperature pressure, is 68 degrees at sea level, so 1 atmosphere. And so this is important to understand why your meter may respond differently from one confined space to the next, because the ambient temperature might fluctuate. Your pressure may fluctuate if you're going from site to site. And so those are all of your LEL and your UEL readings are based off of NTP or STP, but again, there's only 8 degrees variance on that. And so you have to adjust to this concept based on your site specifics. As you add more oxygen to it, your flammable ranges get wider. And also understand that when you have a UEL situation, so I open up a confined space, I open up the hatch, or I pull the cover off the opening, that if I have my first reading show that I have a UEL situation, an upper explosive limit, it's up in the upper range, then I will always pass through that flammable range in order to get back to zero get back to the safe zone. And so I open up that hatch, my initial readings may be high, I ventilate, whether that's mechanical or natural means, whatever means of ventilation you want to use, my concentrations will start to adjust, and then I'm already passing through that sweet spot, that flammability range, so keep that in mind. Most of your meters, if not all of them, most of your meters should be intrinsically safe, but are your ventilation fans safe or intrinsically safe? Are they rated for an intrinsic or flammable atmosphere, potentially hazardous location? And so understand that simply opening up that hatch or that cover on confined space may be all it takes to create that flammability range.
Absolutely. And something I think everyone should be keeping in mind, especially looking at the screen right now of gases lighter than air. A lot of these are byproducts or even primary feedstock, elements of feedstock for a lot of renewable fuel. And with the changing scope of energy right now, we are seeing a lot more different types of renewable fuel, from solar, ethanol, biodiesel, wind. A lot of those components will involve many of these chemicals that are lighter than air, and making sure that whatever equipment you are using is suited for those applications so that you can put in the best protection programs possible.
Absolutely. And so looking at our standard alarm threshold, so generally your manufacturer's default is based on the OSHA's PELs, your permissible exposure limits. And so your PEL is your exposure to an 8-hour workday, 40-hour work week, in which you should not have any adverse health effects, or up to 95% of the population will not have any adverse health effects without wearing any kind of PPE. And so there may be situations where you want to adjust that. You want to adjust that threshold. So let's say that your carbon monoxide on your meter, the PEL is 50 parts per million. However, NIOSH's REL, the recommended exposure limit, is 35. Maybe I'm working around carbon monoxide and I want to adjust it to be more sensitive, or I'm working around hydrogen sulfide and I want to adjust it from 20 parts per million down to 10, or 10 down to 1, whatever it is. You need to understand what it's based on, your company requirements and your site-specific hazards. Maybe you get the meter right out the box and it's just fine, but maybe again, based on your site-specific hazards and your hazard assessment, maybe you need to adjust that. Your time-weighted average, your instant, your short-term exposure limits, those are typically all on there. Is there a project work or exposure that may need different alarms? Again, understanding what it is. And so I'll let Rebecca talk about the Dräger vision here in a second. But one of the things on here is not only understanding what your alarms will set at, but also understanding what those different alarm levels mean. And so there, you have your low alarms, you have your high alarms, and there's a certain point where it just gets crazy. And so it's important to understand your different alarm levels. And so let's say we're using a catalytic bead sensor, your Wheatstone bridge, and we're in a situation above the LEL. Those catalytic bead sensors will only read up to 100% of that LEL. So if I'm reading, let's say methane, just to keep it simple here, let's say I'm looking, I know I'm looking for methane, and methane LEL, the lower explosive limit, is 5%. It will only read up to 5% of that concentration. And once it hits that 100% LEL, which is 5% of the concentration, it's going to stop. And so if I get something above that, or something that's way above my UEL or in the high range, a lot of meters, not all of them, but a lot of meters will essentially, I'm using air quotes here, they'll lock out the meter. And so what happens is my low alarm, your first level, it starts going off. It says, hey, I'm beeping. More or less, I say, hey, shut up, and it shuts up. My high alarm is a latching alarm, which means I push the silence button or somehow to silence. It's not going to shut up. It's going to keep going off until I get out into a fresh air environment. And then you'll get to a certain point on the flammability range where it more or less goes into a protection mode. And it essentially shuts off that sensor and says, I'm not shutting up until you go outside, you shut me down, and you reboot me from scratch. And so understanding that if my sensor won't silence, then hey, I'm in a high alarm or a latching alarm, and I need to understand what the severity of that actually is. And so, Rebecca, if you want to talk about the CC Vision, I know you've got some more experience on that program of software.
Yeah, and Draeger CC Vision is one of the ways that Dräger as a manufacturer offers for the gas detection to be calibrated or changed. So like Drew was saying, if the OSHA PEL is not the standard threshold that you want to set, Draeger CC Vision is one of the ways you can go into that, as well as gathering a lot of data, reporting, sensor lifespan, many of those things. But we advise obviously that you consult with the manufacturer of whatever product you're using so that you understand how to set your meter or your gas detection equipment to the appropriate threshold that you and your company find to be best for your operating environment.
Absolutely. And so this is just one of the Dräger meters, the 8000. We'll look at some of the specifications on this. And so again, every meter is a little bit different. So it's important that you reference your operator's manual or user manual to understand which one it actually is. And so if you look at a lot of this stuff can be found, typically the reference as technical data or technical specifications when you open up your manual. But you can look at this, and this is where you get those T90 response times, those T50 response times, understanding the range that it actually works in, and then how small of a resolution it will actually go down to. So look at this particular meter, the one you see on the right. So your oxygen sensor on that particular one will read from 0 to 25% oxygen in 0.1% resolution. Typical response time at T90 on that is less than or equal to 15 seconds. It may be 15 seconds, it may be 3 seconds, just less than or equal to 15 seconds. Going to carbon monoxide, 0 to 2000. I've seen a big fluctuation on both the carbon monoxide CO and the H2S sensors, because carbon monoxide, there may be some meters that will read 0 to 300, 0 to 400, some that are reading 0 to 2000. So they're all a little bit different. Typical response time on that is around 20 seconds, less than or equal to 20 seconds. H2S, pretty much the same response time on that one. And then your combustibles, explosives, your LEL sensor, again, that's reading 0 to 100% of the LEL. And then they have also in this particular meter is a T50 response time of less than or equal to 15 seconds, and then less than or equal to 20 seconds for the T90. And to kind of focus on that T50, T90 while we're here, what that actually means is how long does it take to get more or less in a nutshell, how long does it take to get a 90% accurate reading based on your environment? And so I need to give that meter, that sensor within that meter, time to send it through that catalytic bead sensor. I need to give it time to have that actual reaction, produce that reading on my display. It's not instantaneous. Now, even though 15, 20 seconds, it may sound like a little bit of a wait. I can remember doing about 10 years ago, getting called out requested to do an air monitoring class for a customer, and they call me up and they tell me what kind of meter it is. I'd never heard of this meter. It was, never heard of it before, never seen it used. And so I called the manufacturer and I said, hey, I'm needing the T90 response times for this particular meter. And the first thing they said, this is their reps, the first thing they said was, you still have that thing? And that's my red flag there. But they had a single gas ammonia sensor, and the ammonia sensor, the T90 response time for that was 300 seconds, 5 minutes. I can almost guarantee you there was a lot of pencil whipping going on at that point, because that would mean if I'm going into a vertical space, that I'm waiting 5 minutes, getting my reading, dropping it down four more feet, waiting 5 minutes. Like let's just be honest, it's a long time. So we've come a long way. I mean, 5 minutes to less, it's again less than or equal to 15 seconds, less than or equal to 20 seconds. That just means that's the max. And so it may be done in 2 or 3 seconds, but that just gives you a heads up, a general idea. And again, refer to your user manual, operator manual, to see what the specifics are for your individual meter. And that will tell you, if it's an infrared meter, or if it's catalytic bead, Wheatstone bridge sensor, or an infrared sensor, it'll tell you based on each individual sensor what that T90 or T50 response time is. So it's important to make sure that you're looking at the appropriate time frame.
Absolutely.
And so now that we go into our confined space, we need to verify what our readings are, whether they're good, whether they're bad. We need to make sure that we understand that we're verifying those. So understanding you have a working knowledge of what you're working to know what you're actually going to expect in that confined space, right? And so knowing that, I'm going into a confined space and I should be expecting hydrogen sulfide because of what product's in there, or I should be expecting some kind of off gas to be in there. Whatever it is, I need to know what I'm actually expecting in there. Am I getting negative readings? What's causing that negative readings? I had a friend reach out to me a couple weeks ago, or about a month ago, I guess now, and show me his 4-gas meter was getting like a -3 parts per million on his sensor, and he's like, why in the world am I getting a negative reading? What should be going on there? Sometimes it may be as simple as a fresh air calibration. You may have calibrated it in a contaminated atmosphere, and so I kind of joke about about some experiences we had at the firehouse before. Had some rookies jump off the fire truck. We get called out to a carbon monoxide alarm at a residential house. They get off the fire truck and they hop out the fire truck, and they're standing right next to the exhaust pipe doing a fresh air setup. So they're getting carbon monoxide from that. And so what that's doing is that's giving a improper calibration. So it thinks that if I've got, let's just say 20 parts per million of CO being pumped out, it's going to essentially think that everything up to 20 parts per million is 0. And so maybe I did a fresh air calibration in a contaminated atmosphere. So if I get those negative readings, let's just try going out to a fresh atmosphere and then doing that fresh air setup calibration again. Try that again. Maybe I get some kind of negative cross interference. So there may be, depending on the sensor, may be cross interference on there that just naturally does that. So I may have a sensor that is designed to read chemical A, but if it sees chemical B, it's going to give you the opposite of the spectrum. So rather than 5 parts per million, it may give you a -5. And so again, referring back to your technical specifications, a lot of times those sensors will tell you, or that sensor information will tell you what those potential negative cross interferences are. And so, engage other team members to determine kind of the, what's the relevant activities in your area. And if you have 2 monitors next to each other, use those, but understand, again, we talked about earlier, you may have 2 different readings, just depending on the technology of that meter that you're actually using. If you're using a, catalytic bead sensor versus an infrared, and versus that, some other kind of technology, it may be completely all 3 different readings, and understanding why that's taking place, which one is accurate, and then how do you verify that it's accurate. And again, these are all meters and they work perfectly, but they're still electronic. And again, it doesn't hurt to pull out, if you have a Dräger tube or something, colorimetric tube, to pull that out and actually verify that. I personally use that to where, I've worked at companies that have used dry ice for their packaging, which is carbon dioxide. It's putting off this off gas, and I go out there and measure it, and I'll take a 4-gas meter, or I'm sorry, 5-gas meter that had carbon CO2 on there, and my CO2 readings are like through the roof. And so, nobody's complaining of anything. I start, asking people are out there any symptoms, and they say they're all fine. And so I go back to talk to some of the maintenance, and they say we've never had that kind of high reading before, and I'm getting these readings off the bat. And so my first thing is I go back and I go try to calibrate the meter, grab 2 other meters, and took 3 with me actually, and kept getting the same exact thing. And so, there ended up being a problem with the type of meter they had. And so what we ended up doing is I ended up getting a Dräger tube out, taking one that was designed for carbon dioxide, went out there and got a more accurate reading. So again, having those multiple methods and multiple avenues of figuring out how to verify that reading is crucial.
Absolutely. And that's one of the things, situational awareness, if you will, or environmental awareness for the fresh air calibration. especially if you're working on projects or turnarounds where there's a lot of tight spaces, a lot of cranes, heavy equipment, from forklifts to vacuum trucks, nitrogen trucks, a lot of exhaust going on in combination thereof with a lot of particulates being generated from welding or potentially refractory dust, silica, so on and so forth. So finding a good fresh air location to do that fresh air calibration is really going to make a difference in those readings as well. So great point.
Yeah, somebody just sent a thing in the chat about don't hold the sensor up to an exhaust pipe to see if it's actually working, and that it will bust the sensor. I mean, it's just like with the UEL thing we were talking about. It'll lock it out, it'll flood it out. So do not expose it intentionally to a high atmosphere just to see if it's working. And so here we have an example of a confined space assessment. I mean, they come in all shapes and sizes. You can put it on literally any format you want. This is one that I'd created for a customer years ago. And so we create this, and we'll go through, we'll put the space ID. So that's just whatever identification number they have for that particular confined space, the name of it, the location, the floor. And then I had it at the time when I did this, whether it was labeled as permit required or not, and then went through and actually marked whether it should be permit required. Atmospheric hazards, so O2, CO, H2S, LEL, should I expect to see those there? So I can look at this right off the bat and see, okay, should I expect to see some kind of oxygen issue, oxygen deficiency potentially? Should I expect to see CO in here? Engulfment hazard, entrapment, so on and so forth. And then capacity of it, your gallons. And so we look at these, again, they all come in different shapes and sizes, so but you should be having some kind of evaluation for your confined spaces. If you're a contractor, you're going to other customer sites, they should be having this, because this is a requirement by OSHA's 1910-146, is that you have to properly evaluate all of your confined spaces for hazards. And so, again, they may have something, on a spreadsheet, they may have a form individually for each space. But if I'm going into a space, I need to make sure that I'm at least reviewing this to know what I'm walking into. That's how I'm going to verify my readings. If I look at this confined space hazard assessment and it doesn't have hydrogen sulfide checked, and then I go back in that space and I'm getting high hydrogen sulfide readings, hey, something's out of the norm here. Something is producing that hydrogen sulfide that shouldn't be in here. Is it something that I'm doing that, whether I'm creating that external source, or is it something that's inside that space and I'm unaware of? I need to figure out what that actually is.
Absolutely. And coming from refining and predominantly downstream petrochemical and chemical facilities, we've taken this even more in depth, which there's all, like Drew said, there's all shapes and sizes. Just understanding not only what was in the space prior to, what to expect to see, but the type of work that might be going on in the space. And we kind of touched on that in the confined space entry critical thinking webinar. But even so much so down to the actual task. A lot of times you have different service companies going in. You might have the first one to go in that's going to be cleaning it, neutralizing it. You might be removing some materials, and then the next contractor going in is going to be welding. And each service company is going to be creating different types of hazards and reacting and causing different type of hazards inside those spaces as well. So keep that in mind as you think through, you do your hazard assessment and you plan, and please reach out to us if you'd like any help as well. That this is ever growing, ever changing, and continuously dangerous. And so it's very important not only that you have the proper equipment, but you have the proper planning and assessment in place so that you can really get an understanding of how to be prepared for anything that may arise in those spaces.
Absolutely. And so if we do get low or high readings, we understand how we're going to react to those and why we're getting those. So again, we can look at the hazard assessment and the confined space hazard assessment and try to figure out, is that actually taking place? Should I be expecting that? But some of those factors that may play into it is what's stored in the confined space. Is it the normal product? Are there gases that are being released whenever I'm cleaning up? Is it the cleaning materials itself? Are they doing some kind of installation inside of that confined space? We've had situations to where a contractor's coming in and replacing a new flow meter on a level sensor on one of our tanks, and they're using all this resin and epoxy and all these different things to kind of get that seated into the tank. And so they're creating their own hazards. They're bringing that into it. Materials absorbent into the walls of confined space that were either there before, maybe previously, and I'm reusing a tank, and then decomposition or oxidation of the materials. And then of course the work that I'm doing inside of it. Am I doing some kind of hot work? Am I doing some kind of painting or degreasing? Is what kind of ventilation issues do I have? You know, I've even seen some companies that will put some of those, you know, Venturi air blowers on top of all their tanks, and then all they have to do is flip a switch and that thing comes on and starts working. And so those things, you know, works great, but you know, what am I relying on natural ventilation alone, which in most cases, especially in emergencies, is not going to be sufficient, or am I going to have some kind of mechanical ventilation, positive pressure, negative pressure, whatever that may be, and then looking at whatever's around that confined space. I mean, it's simple to say that maybe some coworker or contractor or whatever it is sitting next to the tank where they're sitting in the truck because it's cold outside and they're taking the break in the truck with the truck running, and now I'm sitting there with that exhaust pumping inside of that confined space. But what else outside of that is adjacent to that area that may play into a factor? And then going on to how we mitigate that on the next couple of bullet points. How do we mitigate those issues? How do we verify that their isolation points, are they causing that issue to leak by? Has my ball valve that I've locked out, is that actually causing that to leak past it? Do I need to get increased ventilation in place? Do I need to, add a second fan, or do I need to use those ventilation fans in tandem to where I have one using positive pressure and forcing air in, and then I have one at the bottom of that confined space that's using negative pressure to suck that contaminated air out? And so do I need to go in and clean it out? A lot of different things here that we can focus on, looking at wind speed, process upsets, all those different things there that we're taking into mind based on that site-specific hazard assessment, how we're going to mitigate that.
Absolutely, and great points. So I had another game for us to do, but in the interest of time, so that we have enough time for some questions, we're going to skip that. Drew had pulled this OSHA letter of interpretation. Drew, I'll let you touch on this for a moment.
Yep, absolutely. And so this is a letter of interpretation regarding OSHA's confined space standard 1910-146. And so they asked if a confined space has an atmospheric concentration of a subpart Z contaminant over its PEL, but it's not capable of causing death, incapacitation, impairment of ability to self-rescue, injury, or acute illness, would this meet the definition of a hazardous atmosphere? And so they came back and said just because it's above the PEL does not necessarily make it a hazardous atmosphere, right? And so they're looking at hazardous atmosphere. They're focused on just what was in their question. They're focused on just what's going to cause death, incapacitation, impairment of ability to self-rescue, injury, or acute illness, so short term. Those PELs are focused again on 8-hour work weeks, 8-hour work days, 40-hour work weeks. And so they're looking more at the chronic, the long-term effects. And so this is where we need to reference our SDS, or safety data sheets. We need to reference the chemical, the composition, how it functions, more or less the chemistry behind it, how it actually affects your body, the target organs. I need to look at all those things. So just because it's above the PEL doesn't necessarily mean that it's a hazardous atmosphere, and that in that case will make it a permit required. Although it can, just notice it doesn't always do that case.
Yeah, absolutely. And the more you dig into that, you'll actually see the reverse in some cases, that just because it's below a PEL does not mean that it is not a hazardous atmosphere. The conversation of confined space especially changes things rapidly. There's also, which we'll get into further in our next webinar, but there's also a discussion between toxicity and flammability. Sometimes you will actually hit toxicity before you hit flammability, and that presents a whole different set of concerns of how you're going to make that assessment for that work.
Absolutely right.
So next time we're going to focus on which monitors to use and when, and diving more into their limitations and understanding some of those things such as cross sensitivity, a little bit more onto the calibration, the wear and tear, and the environment that the monitor is used on, and dive into more of that. So we hope you join us for the next one. And now we'll switch over to answering some questions. So Ryan, do we have any questions for us?
Yeah, we sure do, Rebecca. I had a couple of questions come directly into my chat box, and I had a couple of emails when we sent the communications out, letting everybody know about the webinar. So hold on tight. We've got 3 of them. And by the way, well done, Rebecca and Drew. Thank you for putting this together. Y'all knocked it out of the park. So the first question that came in the chat box is this: are there any specific training OSHA requirements for someone conducting air monitoring?
So I can take that one. So OSHA does not specifically mention any training requirements for personnel, conducting air monitoring. So nothing within OSHA. However, I always like to reference the NFPA standards. One, it's from being with the firehouse and the fire department, but also NFPA gives you a lot of the how do I meet these OSHA standards. So NFPA 350, which is their guide for safe confined space entry and work, they do have a specific chapter regarding air monitoring within confined space. Gives you specific duties, responsibilities for what they refer to as gas testers. And within that same chapter, it has a section focusing on gas tester qualifications and demonstrated competencies. And so, as a recommended best practice, you should refer to NFPA 350, and you can just create an online account. Now, you have to pay if you want to buy a hard copy, but anybody can view those NFPA standards online for free. And so, I would recommend at least referencing those standards because it'll tell you again qualifications and competencies, so that when you say that somebody's qualified to operate a gas meter, what are you actually qualifying them in? How are you actually gauging that? So that gives you some guidance on how to evaluate them. Good question.
Yeah, I think that answers that pretty well. The second question that came in the chat box is, if the OSHA letter of interpretation you mentioned says that just because a chemical is above the PEL, doesn't it mean it creates a hazardous atmosphere? What should we be referencing?
Right. So, just like we mentioned a little bit earlier, that PEL is just referencing the 8-hour work days, 40-hour work weeks, that long-term exposure, that long-term exposure, that chronic limits. And so the way the 1910-146 standard defines the hazardous atmosphere, it just says that it may expose employees again to that risk of death, that incapacitation, impairment of ability to self-rescue, and so which is more or less able to escape unaided from a permanent space, injury, or that acute illness. And so if it's not going to cause any of those things, then they're not covered by that. So the key part here is that bottom note, or that portion of what it's covering, so that incapacitation, risk of death, so on and so forth. And so what we can do, is reference those short-term exposure limits, reference those recommended exposure limits from NIOSH, the TOVs. If I'm at a confined space for just a quick 5 to 10 minute inspection, and I'm at a concentration of 55 parts per million of CO, the PEL is 50 parts per million for that one. If I'm at a 55 parts per million exposure right now, more than likely it's not going to cause any acute illness for 5 or 10 minutes. Now, if I'm in there when it's 155, then sure, that might be a concern. And so it's really going to be specific to the type of atmosphere you're in, what you're going to be doing, how long you're going to be in there. And so there's a lot of factors to play in there, but definitely be referencing your other regulatory limits. Like I said, your RELs from NIOSH, your TOVs from the ACGIH, and then understand how long you're going to be in there. Again, 5 to 10 minutes at one level versus 5 to 10 minutes at something completely higher is a whole lot more different. So good question.
That's great. Thank you, Drew. And really this last one is less of a question, more of just a statement. And this individual says, I'm interested in oxygen detection and alarm systems for oxygen deficiency and CO2 detection for dry ice storage areas. So, Rebecca, Drew, I don't know if you all have a closing slide with your contact information, but now might be the time to pull that up. And it looks like most everybody is still on the webinar, and if everybody can take note of Rebecca's telephone and email address. If you have any follow-up questions, please either give her a call, shoot her an email. I know her and Drew are pretty excited to help you all out. And with that, again, Rebecca, Drew, thank you for your time. Everybody who's on the webinar, we hope you enjoyed the time that you spent during the last 40 to 50 minutes, and we look forward to seeing you at the next webinar. I hope everyone has a good rest of the day. And once again, thank you to our presenters.